And hello, guys. I hope you all are doing well. So let's continue our conversation about momentum methods. Right? That's what we were talking about. At least that's what we've been talking about for last few classes. So we introduced momentum methods as methods that we basically, when we're using those methods, we're looking into the relationship between the time integral of forces and change in the object's momentum. Right? We started with principle of linear impulse and momentum, going from Newton's second law, right? There's nothing new there. We started from Newton's second law, and we derived the expression for principle of linear impulse and momentum. Basically, linear impulse is equal to change in linear momentum. Linear momentum being mv. And we went over a couple examples. One thing I want to mention is that remember momentum methods and energy methods. The difference is that in momentum methods, right, we care about the directions, right? We again go back to a point that we look at everything as vectors, as opposed to energy methods where we were looking at velocity as just a magnitude of velocity. Remember, we had v squared, so we didn't really care that much about direction or the velocity as a vector. We were not really focused on that. But in momentum methods, again, we have to remember that velocity is a vector, force is a vector, so directions matter again when we are using momentum methods. Now, we talked about principle of linear impulse and momentum, went over a couple examples. Then we introduced principle of angular impulse and momentum. Again, the expression for that, we derived that expression by starting from Newton's second law, right? We came up with the expression, the relationship between angular impulse and change in angular momentum. Angular momentum being r cross mv. Mv is the same as mv for linear momentum. Now in angular momentum, we multiply that or find the cross product of r position vector, wherever or object or particle that we're studying is in some coordinate frame. Find the cross product of that and velocity as a vector. Right? And that was the main difference between principle of angular impulse and momentum and principle of linear impulse and momentum. Over there was no discussion of position. It was the relationship we had between basically force, the integral that we were calculating over time in a time for the force and the change in linear momentum. Here we not only have that integral of force over time, we also have position vector where the object is during the motion. Now, putting this principle into words, the angular impulse applied to an object during an interval of time is equal to the change in object's angular momentum. We said angular momentum is a vector because it's the result of the cross product of two vectors, r and mv. And to find the direction of angular momentum, we use right-hand rule. As long as you know r is a vector, v is a vector, m is just a constant. So mv and v, they have the same direction. As long as you know r, use right-hand rule, four fingers in the direction of r vector, right? Palm of your hand facing or in the same direction, better to say, of your velocity when you make your fist. Your thumb shows the direction of angular momentum, right? That's how you can find the direction of angular momentum in three-dimensional space or in the space generally, right? And just keep in mind that the angular momentum is also a vector because it's a cross product of two vectors. Now, we introduced a special case, central force motion. Now, what was a central force motion? We introduced that as a kind of motion in which during this motion, the direction of the resultant force, whatever is the resultant force on your particle, on the object or particle rigid body you're studying, the direction of this resultant force always stay toward a point, fixed point. Right? Basically, that's the definition. So it doesn't matter where your particle is, the direction of the resultant force stays toward a fixed point in your frame, in your reference frame. You need a reference frame because you're dealing with position r, right? So towards that reference frame, doesn't matter where your particle goes, this force always remain toward some fixed point relative to that reference frame. If that happens, then the left side of this equation here, right, this expression becomes 0, because that's the cross product of r and f. So if r, vector r, and vector f, they always have an angle of 180 degrees, right? This cross product becomes 0. What is the cross product? Cross product of a and b is like ab sine theta, right? The angle between two vectors, and these two are vectors. The angle stays 180 degrees no matter where you go. It's a central force motion. So the left side becomes 0. Angular impulse becomes 0 during this motion. That means that you have a constant angular momentum, right? You can think about it as a conservation of angular momentum. Angular momentum stays constant during this motion. So for any given point during this motion, the angular momentum is the same. That means that if you write the relationship between angular momentum for 2 points, the angular momentum for 2 points, for any 2 points during this motion, should be equal. Right? And that's basically what we got here. So the angular momentum stays constant, or better to say, the angular momentum for any 2 points during this motion, the angular momentums are equal. Now we said that it's easier, or it's better to, when we have a central force motion, it's better to study this motion using polar coordinate system. You have your xy coordinate, just use your polar coordinate, er and e theta, represented with these two unit vectors. If you do that and follow the expression, basically plug in the values for velocities in r and theta direction, er and e theta, do the cross product, what happens is that you're going to end up having the expression of r1 v theta 1 is equal to r2 v theta 2. r1 and r2 being the position vector representing where your object, rigid body, or particle is at point 1 and at point 2, respectively. V theta 1 is going to be the angular velocity or transverse velocity, velocity in angular direction, in theta direction, however you want to refer to it. V theta 1 is that, and V theta 2 is the angular velocity or velocity in theta direction at point 2. Right? So that is what you get from the fact that you have a central force motion. As a result, in that your angular momentum is constant. So we went over one example. We looked at, we had a central force motion. We looked at how can we use the fact that the angular momentum is constant and angular momentums at 2 points are equal during this motion. We use that to find the velocity. Right? And I started the second example. I gave you the problem statement. The idea was that we have a 2 kilogram disc sliding on a smooth horizontal table, meaning just forget about the friction when we talk about smooth, when we see smooth. This disc, 2 kilogram disc, is connected to it's connected to a hook, right, somewhere on the ground, like through a cord, elastic cord passing through a hole. Right? Now, we said the force or tension force in this cord is a function of radial position of this disc on the table. T is equal to 6R. So if you're all the way in the center, R is 0, no tension in elastic cord. The farther you get from the point in the middle or that hole, the higher or the larger this tension force in your cord. Now, we are given some information. We're told that if the disk is at r equals to 1, like 1 meter away from this hole, at that point, when it's there, we give it a 4 meter per second initial velocity. Right? Some initial velocity, I show that with a green arrow. We give it some 4 meter per second initial velocity in theta direction, or as they mentioned here, in transverse direction. It's the same as theta direction. This starts moving, this disk, or increases, goes from 1 to 2 at some point. Now, we are asked to find the components of velocity, like radial and transverse components of velocity, r and theta, vr and v theta, when we are at point 2. At point 1, we know these components. R component is 0, theta component is 4 meters per second, because we gave the velocity, initial velocity, in 4 meters per second in transverse direction. So we know where the position is. We want to find out what is the velocity at position 2. Right? So it fits into the whole category of momentum methods. Right? We know is the position, initial position, final position, and we want to find out what the velocities are. Right? And if you pay attention, and if you've been paying attention, better to say, let's look at this from the top. This disk and its motion with respect to this hole in the middle of this table, if this is R, and let's say this is the motion, it's a central force motion. Right? If you can take this as ER, take this as E theta, right? And the force applied to this disk from this cable, elastic cord T, during this motion, no matter where this disk goes. And remember, this is in horizontal table. So with gravity, weight downward, normal force upward, we don't really care about those. Normal is equal to weight. That's in, if you want to think about it, in Z direction. So this force, because of this cord, right, if you draw the free body diagram for the disk, it always, during this motion, it remains toward this point in the center, this hole. Right? So this is central force motion. It always stays in this direction, or better to say, the angle between the force and R vector is always 180 degrees. They're collinear. Right? That means we have a central force motion. That means HO2 is equal to HO1, right? Or more formal way, angular momentum stays constant. Right? So since we have a central force motion, HO2 is equal to HO1. Now, this is, we said we use polar coordinates when we're dealing with central force motion. So let's continue that. We derived that for the central force motion in polar coordinate. We said R1 V theta 1 is equal to R2 V theta 2. See what we have. We know R1, we know R2. We also know V theta 1 is 4 meters per second. Right? So from there, you can actually find V theta 2, the component of theta for velocity at point 2. Right? That would be R1 V theta 1 divided by R2. R1 being 1 meter per second, R2 being 2 meters per second, V theta 1 is 4. So from there you get V theta 2 is 2 meters per second. Right? So this is the transverse component of velocity at point 2. Now we have to also find the radial component, right, to be able to actually get the velocity. How do we do that? Well, looking at what we have in the problem, or the problem statement, we have position, we have velocity, and we have the relationship between force and displacement or position. T equals to 6R. So let's see what we can do. Looking at principle of angular impulse and momentum, right? We used that already, and it only gave us V theta. So there is nothing really more there we can take advantage of. There's nothing really there we can use. Principle of linear impulse and momentum. Well, to use this, we need to know the relationship between force and time. We have to be able to calculate this linear impulse, the integral on the left side. We don't really have that. There is no torque about time in this problem statement. So what do? We have a relationship between force and position, right? Remember, when we had the relationship between force and position, we could use energy methods, right? That was the whole idea of energy methods, relationship between force and position and velocity, right? We're finding that integral from R1 to R2 resultant force dr, and then the change in kinetic energy. So we have to use, this is a problem that you use both momentum methods and energy methods, specifically to find what you're asked to find. Right? So that's why I brought this example here. So you have to kind of be able to look at the problem statement, see what you're given, and think about what with this information, what kind of method you can use to get to what you want. Right? You can't really use linear impulse and momentum because there is no conversation of time here. Right? So since you're talking about the relationship between force and position, think about energy methods. So I'm going to use the energy method now. See, where does that take me? Let's see. From R1 to R2, FDR, right, is equal to 1 over 2 m v2 squared plus, well, minus 1 over 2 m v1 squared. Now remember, v1 and v2 are, we are in polar coordinate system, right? So v1 is vr er plus v theta e theta. And v2, same story. You can think about this vr1 v theta 1, and this is vr2 er plus v theta 2 e theta. Right? And the force, the only force in this scenario is T. Right? The force applied to this disk because of this elastic cord. So I'll plug that in too. So let's plug in everything. So from there, I'll get relation. This integral R goes from R1 from 1 meter to R2 from 2 meters. 6R dr. Let me write everything down here, so I have space. So integral from R1 from 1 to 2 R2, 6R dr is equal to 1 over 2 m. Now v2 squared, I can actually write it here. So v2 squared, we have v2 right there, right? So v2 squared is going to be vr2 squared plus v theta 2 squared. Right? Don't believe me? Do the multiplication. You can think about v2 squared as, let me just do it for at least one of them. v2 squared as v2 dot v2, right? Two vectors. Let me just write it somewhere with more space. I can erase it later on. Just want to show you what happened there. So if we have v2 squared is v2 dot v2, right? Two vectors. v2 is a vr2 er plus v theta 2 e theta dot vr1 er plus v theta 1 e theta. Right. Now do the dot product. Right. This multiplied to this multiplied to this multiplied to this, and this multiplied to this one. Right. So from the first one, right, you will get, so from there you'll get VR2. Oh, this should be 2. And we theta 2 plus now V2. So VR2ER times VR2ER, right, becomes VR2 squared. VR2ER V theta 2 E theta ER times E theta is a dot product of two vectors perpendicular. Remember, what is dot product? A dot B is AB cosine theta, cosine between them. So if you have two vectors that are perpendicular, cosine 90 degrees is 0. So that becomes 0. Same story about V theta 2 E theta times VR2 ER. Right? E theta dot ER, two vectors are perpendicular, dot product becomes 0. And again, V theta 2 times V theta 2 E theta times V theta 2 E theta. These two, E theta 2 times E theta 2, the angle between two same unit vectors is 0, cosine 0 is 1. So this becomes plus V theta 2 squared. All right, so that's how V2 squared becomes VR2 squared V theta 2 squared. Same story for V1. You can just write and do the cross dot products, and you'll get a V1 VR1 squared plus V theta 1 squared. Hopefully that makes sense to you. All right, so we plug in those values. So say 1 over 2 mv r1. Well, I was putting 2, so let's follow that. VR2 squared plus 1 over 2 mv theta 2 squared minus, right, this is the first, this is the second one, 1 over 2 mv r1 squared plus 1 over 2 mv theta 1 squared. I'm also clearing this up. So let's see what we have here. We can calculate actually calculate the left side. It's a pretty straightforward integral. This becomes. Let me go to the next page. So this becomes. Next page. Let's go there. So the integral becomes. Let's write it this way: 3 r squared from 1 to 2, right, is equal to, the right side was 1 over 2. I can actually take m out, is a constant. This is VR2 squared plus V theta 2 squared minus VR1 squared plus V theta 1 squared. Right? 1 over 2, m is given. This is 2 kilograms, right? Let me fix that. This is 2 kilograms, the disk. So that is given times 2. Velocities, we don't know what VR2 is. That's something we're looking for. V theta 2, we found it. Right here, this is what we found. V theta 2 is 2 meters per second, so 2 squared minus VR1. There is no radial direction for velocity. This is 0. Minus V theta 1. Theta 1 is 4. It's given, 4 squared. So this becomes r squared 4 3 times. So this is 3 times 2 squared minus 3 times 1 squared is equal to 1 over 2 times 2. It's gone. This becomes VR2 squared plus 4 minus 16. Right? From there, you can find VR squared, VR2, that is 9 minus 6, 4, 9. This becomes 9 plus the other side. You have 4, let me just make sure. Then you have, oh, let me write it in a proper way. So VR becomes, from this side, you get 12 minus 3, so that's 9, minus 4 plus 16. From there, VR squared becomes, you get 12 from there, 12 and 9, 21 meter per second. This is VR2. So you get your V at V2. Right? V2 is VR2, 21 ER, plus V theta, which is, theta is 2. So 2 E theta. And that's going to be your velocity at 2 with its components. That's what we're looking for, right? Radial and transverse components for velocity. Right? So we started with principal angular impulse and momentum. Use that to find the theta component of velocity at point 2. Then we looked at what we had. With the information we had, we could actually use energy method to find the R component of the velocity at point 2. Right? You could start with energy method, find the velocity at point 2, and then knowing the velocity, you probably could V theta 2. You could do it the other way around. Still, you would have gotten the same answer.